Hi guys, today we'll be doing LeetCode challenge. Minimum cost to make at least one valid path in the grid. So we'll be given a grid with the m column, m row and column. So each cell of the grid has a sign pointing to the next cell you should visit if you are currently in this cell. So basically, if the grid has value 1, you can go to the right cell. 2 means you go to the left cell. 3 means you go to the lower cell. 4 means you go to upper cell. Right? So you will initially starting at the top right corner, and our goal is to reach the bottom left corner. Top right. This is top left and reach the bottom right. Okay. So we need to calculate the minimum cost to make the grid to have at least one valid path. So what you can do here is that once you reach basically this cell, right? So you cannot go anywhere else rather than go out of bound, right? You must go down. So you can modify the sign on the cell with the cost of 1, and you can modify the sign on the cell one time only. So basically, then if we reach a case where we cannot go anywhere else, and we can change the sign to go to the next cell. For example, if we are at this cell, right, we can change 1 to 3. So now we can go to the lower cell and continue with our path. So we need to return the minimum cost to make the grid have at least one valid path. So for this example, then basically what we can do is that we can go like this. We change this sign to a lower, to 3, to go to a lower cell, and we continue this path. We change this sign to 3, go to a lower cell. This, change this to go to a lower cell. Yep. And so basically the cost here would be 3, right? So basically then we can think of Dijkstra here. Why Dijkstra? Because you basically can think of each of these cells as a node. And one node can have a maximum of 4 edges, right? So basically for this node, there will be 4 edges connecting to the 4 node that is vertically or horizontally connected to it. So for example, this edge will have a cost of 0. We have a weight of 0. This edge will have a weight of 1. Why? Because if we want to go to this cell, we have to change the direction, right? And same things happen for this guy and this guy. Okay, so let's take a look at this example. We can visualize it as a node and edge like this, right? So basically then we starting from here. We are starting from here, right? And we want to reach this guy. So we can kind of like think of every cell as a node, and this cell, it has 2 edges simply because it's a corner cell connecting to the right cell and then the lower cell, right? If we move to this guys, and the weight could be 0, but if we move down, then this edge could have the weight of 1. Why? Because we need to change the size of the cell. So if we think it like that, then basically the requirement of the problem becomes find the shortest path from the starting point to the ending point, right? find the shortest path. I hope it makes sense. So now I will code it up. To use Dijkstra, then we need to use a min heap to continuously popping the path with the shortest distance out, and then just do a breadth first search on it, updating all of the neighbor with a potentially new lower cost, right? So we need to initiate our min heap, our Dijkstra array. In this example, then it's a Dijkstra matrix, right? Which will be initially float in C for is in range R, right? Okay. And then what can be the first thing that is going to be pushed into the min heap, right? It's going to be our starting position, right? And then what is the cost to go from this position to itself, right? Basically 0. You can just stay at it, right? And then we add the row number and the column number, and this is basically cost and row and column. Okay, so now we initialize our loop. First things first, we will pop the current path with the shortest distance out, right? So the current is like the cost, we pop. So there are two things that could happen here, right? If we reach the ending point, which means the bottom right of a matrix, right? Then we just return the cost, because we know that is the shortest path from the starting point to the ending point, right? Okay. And if the new cost is actually larger than the cost that we have in our Dijkstra array, right? Then we just continue, because why? Because we have already relaxed this node, right? We have already visited, so we don't have to do a breadth first search on it anymore, right? Else, then if the cost is smaller than the value that we have in our Dijkstra matrix, then we have to update our Dijkstra matrix, right? And then we do a breadth first search on it. We have our direction. So basically, a node can traverse to four adjacent nodes, vertically connected to it or horizontally connected to it, right? For dr dc in and then we will have our new row and new column. So if the new row and new column is inbound, right? So if we need to check, we need to do a check, right? Here's is when we're going to add a new cost to the path. So for example, if we are currently at this cell, we will check the four of the adjacent node, right? If we add this cell, we check, we go to this, we will like basically add 1 to the current cost, go to this, add 1 to the current cost, go to this, add 1 to the current cost, go to this, and add 0 to the current cost, right? So once we visited all the nodes, then we will update the Dijkstra matrix with a current, a potentially lower cost, right? And then add it to the min heap if it is a lower cost. So if our current value is basically at 1, we can go to the rack node without any additional costs, right? And when we go to the rack, means that we increment the column by 1, right? So basically DC is equal to 1, or grid RC is equal to 2, and DC is equal to -1. Because we go to the left, means that we need to subtract from our column, right? Or grid RC is equal to 3, and we go down, means we increment our row by 1, right? So or this is all, okay. Or grid RC is equal to 4, and now we go up, right? In this case, then our addition cost could be 0. Else, then our additional cost could be 1. So we have our new cost equal to cost plus addition cost, right? So we will check with our Dijkstra array, Dijkstra matrix, and if new cost is actually smaller than Dijkstra and RNC, means that we found a new shorter path, right? So what we will do, we will update our Dijkstra matrix, and we push this guy into the heap, right? New cost and RNC, right? Let me check it again. We explore the neighbor, we compute the additional cost, we update the Dijkstra array with a lower cost and push it to the min heap. I think it's enough. Cannot convert string to float int. What happened? What the hell? Oh fuck. This, right? If 1, we go to the right. If 2, we go to the left. If 3, we go lower. Grid RC Let's go to tier 3. N. This is N, right? Yep, okay. Do a quick submit. Okay. Okay, I hope it makes sense to you guys. Okay, thank you for watching, and see you guys later.